Hello friends, welcome back to the channel. This is Ahili Bhattacharya and today we are going to study skewness. Skewness is nothing but the slack in symmetry, as I have written here. See, by the skewness of a frequency distribution, we mean the degree of its departure from symmetry. In formal language, think of it like this. Is your data a perfectly balanced seesaw? Or is one side heavier, making it lean? That lean is what we call skewness. It tells us if the frequency curve is inclined more to one side, meaning it has a longer tail on one side. Now, which way is it leaning? It's super simple to understand. If the longer tail is towards the higher values, it's positively skewed. It's being pulled to the right. If the longer tail is towards the lower values, it's negatively skewed. It's being pulled to the left. And this has a super cool effect on our three best friends, the mean, median, and mode. For a symmetrical unimodal distribution, these three buddies all hang out at the same spot. They coincide basically, which means mean is equal to median is equal to mode. But when skewness happens, they get pulled apart. For a positively skewed distribution, the mean is the most sensitive to those really high values in the long tail, so it gets dragged the furthest to the right. The median, being the middle child, stays in the center, and the mode is the most common value, so it stays at the peak. So the order is mean is greater than median, which is again greater than mode. For a negatively skewed distribution, it's exactly the opposite. The mean gets dragged down by the low values in the long lived tail. So the order is mean is lesser than median, which is again lesser than mode. Remember this, it's a quick and easy way to spot skewness. Alright, so we can see the lean. But how do we put a number on it? How much is it skewed? Let's look at the four main ways we measure it, straight from my notes. First up, Pearson's first measure. The man himself, Carl Pearson, said the difference between the mean and the mode shows us the lack of symmetry. So his formula is SK is equal to mean minus mode by standard deviation. Now let's break this down like a pro. Mean minus mode is what? This is the raw lack of symmetry indicator. Big positive number, positive skew. Big negative, negative skew. But we cannot compare raw numbers between different data sets, right? One might be about centimeter, like in height, another about rupees, like in salary. The scales are different, right? So, what do? We standardize it. We divide by the standard deviation, which is sigma, which accounts for the spread of the data. This gives us a pure unitless number we can use to compare any two distributions. Brilliant, right? Now, sometimes finding the mode is a pain. It's not always clear, so Pearson gave us a second option. We use the empirical relation. Mean minus mode is equal to 3 into mean minus median. Plug that into the first formula. This is the first formula. And what do we get? We get SK is equal to 3 into mean minus median by standard deviation. This is often way more practical because the median is easier to find. Now, here comes the really cool math part. There's a boundary for this thing. We know that in modulus, mean minus median is lesser than or equals to standard deviation. This means, step by step, minus sigma is lesser than or equals to mean minus median, which is again lesser than or equals to sigma. Divide everything by sigma, we get this minus 1 to 1. This is the boundary. Now, if you multiply everything by 3, this part gets SK. Since the last part is our SK, we get minus 3 is less than or equals to SK, which is again less than or equals to 3. Okay? Now, why should you care about this? Because a measure without a boundary is useless for comparison. Imagine a ruler that could be infinitely long. This result that SK is always between minus 3 and 3 gives us a fixed standard scale. If one distribution has an SK of 2.8 and another has zero point 0.5, we can confidently say the first one is way more skewed. This makes it perfect for comparison. Now coming to Bolus measure. This one is also called quartile measure. It's awesome because it doesn't use the mean at all, so it's not affected by crazy extreme values or outliers. For a perfectly symmetrical distribution, the quartiles are equidistant. Q3 minus Q2 is equal to Q2 minus Q1. The distance from the median to the top 25% is the same as from the median up to the bottom 25%. Okay? But When skewness happens, this balance is broken. Positive skew Q3 minus Q2 is greater than Q2 minus Q1. The top section is stretched out. Negative skew Q3 minus Q2 is lesser than Q2 minus Q1. The bottom section is stretched out. Now see, Bowley's formula captures this imbalance perfectly. What do we have here? Sk is equal to Q3 minus Q2 minus Q2 minus Q1 divided by Q3 minus Q2 plus Q2 minus Q1. Okay? And guess what? This measure also has beautiful clean limits, minus 1 to plus 1. Okay? See, how do you write it? You write it like this. Minus 1 is less than or equals to Sk, which is again less than or equals to plus 1. See, Sk minus 1. Sk is equal to minus 1 happens if Q3 is equal to Q2. Imagine that the entire upper half of your data is squeezed into one point. Okay? And for this one, Sk is equal to plus 1 happens only if Q2 is equal to Q1. The entire lower half is squeezed now. Now, alright, last one. This is the most math heavy one, the measure based on moments. Don't worry, we'll keep it high level. In statistics, moment describes the shape of a distribution. The first moment is the mean, the center. The second moment is the variance, the spread. The third moment is what captures the lopsidedness, the skewness. Alright, the formula is what? The formula is gamma 1 is equal to root beta 1, which is equal to m3 by m2 to the power 3 by 2. Okay, now let's simplify that. Since m2, this one is basically what? Variance, sigma square, and m2 to the power 3 by 2 is sigma square to the power 3 by 2, which is sigma cube. It becomes gamma 1 is equal to m3 by sigma cube. The sign of gamma 1 is simply taken as a sign of m3. So we can get 3 points here. If m3 is positive, you have positive skew. If m3 is negative, you have negative skew. If m3 is 0, it's symmetrical. This is the fundamental, behind the scenes way that stats packages often calculate skewness, okay? And that's it. We have covered the 4 key measures of skewness from my college notes. First, Pearson's first, simple uses mean minus mode. Pearson's second, practical, uses mean minus median, right? Range is minus 3 to 3. Third, Bowley's measure. It's robust, uses quartiles, ranges minus 1 to 1. And fourth is moments measure, the fundamental math based approach, right? So now you are pro at spotting and measuring the lean in your data. If you want to understand it visually, I can help you with that. Let me draw a few graphs. See, what is this? This is positive skew. Okay, here this tail is long, so this is my minus or negative skew. And this is what? Symmetrical, as you can already see. So this is the graph-based approach. Now for Bowley's measure, you can understand it like this. See, in Bowley's measure, let me come to this part. Yes, this one. For the graph, you can understand it like this. This part is, let's say, Q1. Let's say this one is Q2. This one is Q3. You can understand the distance for positive skew. And for negative one, how do you draw it? You will take the longer tail here. Here, the longer tail is here, okay? And in this one, the negative skew, the longer tail is here. Let's say this is Q1, this is Q2, this is Q3. You can understand the distance from here. Alright? Now, if this video helped you understand skewness, smash that like button and let me know in the comments. It really helps the channel grow, right? Don't forget to subscribe and hit the bell icon so you don't miss the next topic from my notes. Thanks for watching and I'll see you in the next one. Bye.